Okay, guys, welcome to school. I just wanted to review a little bit. I know we've seen this before, and you probably heard me say this a lot, but let's talk about the first derivative, right? Because um, after today, we're going to be talking about inflection points. So far, we've been looking at functions, right? Imagine this is f of x, right? And it's graphed on the x and y plane. Okay, and so we know that based on this graph, we have 1, 2, 3 critical points. We have one local minimum, one local maximum, another local minimum. And so out of these three critical points, we have basically regions where the function is decreasing, right? So it's decreasing first, then it reaches a local min, then it's increasing again, reaches a local max, and then does that behavior, right? So right now, right, we know that if the derivative is if the derivative is negative, that means that f of x is decreasing. Okay, and if the derivative is positive, then that means that your function f of x is increasing. Okay, and if the derivative is 0, then that means you have a critical point. Okay, and that critical point is either a max or a min. Okay, so we know that. All right, now we're going to be talking about another different kind of point that is also important in our study of functions. Okay, and that point will tell us whether our function is concaving up or concaving down. Okay, so what do I mean by concaving up and concaving down? Concaving down means that your function is basically like this, right? It's going to have a maximum point somewhere right there. Okay, and concaving up is going to be this. So I'm just going to write it. This is concave up, and this is right here, this green is going to concave down. Okay, and you can also, I know it's on the picture, but just wanted to draw that, okay? And so there's a special point in this graph where the function switches from concaving down to concaving up, right? And that special point is going to be my inflection point, which I'm going to highlight because it's a special point and it's a new concept that we're learning, okay? So you have an inflection point when your double derivative, if the double derivative of your function is 0, that means you have an inflection point. So just write parentheses inflection point. Okay, and you can go the other way. You can say, okay, well, the function was concaving down and then it concaves up, or it concaves up and then it concaves down. So it's just a point where your function changes behavior. Okay, all right. So now let's see. I'm going to basically draw the important aspects of this function. Okay, and then we're gonna find out together where the inflection point lies. All right, so the first thing I want to do is I'm going to say, okay, well, this function right here is increasing right there, and then in this region it's decreasing. Okay, and then in this region it's increasing now again. Okay, so I want to make sure that I label, right, with like a little curves, basically this part and this part. Okay, because in this region the function is concaving down. Okay, and in this other region the function is concaving up. Okay, and that means that if the function switches from concaving down to concaving up, there's going to be a special point in between where the double derivative is going to be 0. Okay, and I'm just gonna guesstimate because we're looking at visuals. We're not looking at actual functions like that depend on x and y. This is just a visual, so I'm just gonna say that the double derivative, right, is 0 at that point. So basically my I guess the x where you have an inflection point is going to be 0.4, let's say 0.43. Okay, so that means that the double derivative at 0.43 is going to be 0 because there you have an inflection point. So at x equals 0.43, there's an inflection point. Okay, alright, so let's go on to the next drawing. Okay, so in this function it's not really obvious, right, whether you're concaving up or concaving down. So what I like to do, right, is basically curve it up, right, and there's no way you can keep curving you can keep curving it that way. So basically that's where it stops, and now the other region is going to be that one. Okay, so here you're concaving up, and in the yellow region you're concaving down. Okay, and so the special point in between those two regions is going to be C. Okay, so we're going to say that C is going to be my inflection point. So the question is, which of the label points are inflection points? Then C is my inflection point. And provide a reason, because the function's concavity switches. Okay, and then switches from concaving up to concaving down to concaving up. Okay, so that's self-explanatory. All right, so now again we're looking at visuals, right? So here the first thing I'm going to do is I'm going to draw my curve right here, and that's about it. That's about as much as I can keep concaving down. Then I'm going to draw my other region, which is this one right here, and here I'm concaving up, and there I am concaving down. Okay, so that means that the special point in between those two regions is going to lie, right? Let me use green. It's going to lie right there. Okay, that is the special zone where you switch from concaving down to concaving up. So that I'm going to say that x equals 0. There's a switch in behavior, so f double prime of 0 is going to be 0 because there is an inflection point. An inflection point, okay, and by definition it is a point where the function switches concavity. Okay, so I hope that this was not as confusing, okay, as other videos that I've seen on YouTube, but we're going to be dealing with the visuals first, and then we're going to be doing some examples with actual like functions. Okay, so good luck, and hope you get 100 on your assignment.